Hi, the section 6.3, the prediction and the confidence bands. At first, we introduce some notation. Then after that, I discuss prediction interval and the confidence interval. And we discuss the prediction and confidence bands, that is the two-dimensional version, later. And the prediction by regression line. So once you estimate the parameter beta hat, that is a pair of A hat and B hat, based on the observations x1, y12, xn, yn, then we can calculate the expected value of y0 using the x, basically A hat plus B hat x0. So that is the matrix product of 1, x0 and the A hat and the B hat. So this is exactly the beta hat, the second matrix. But to calculate this kind of expected the value, always we have to use the vector of 1 x0. So this is sometimes not convenient. So in this section, we use the notation x0 is equal to the 1 x0 transpose. So that is 1 x0 transpose. Yeah, so this is the notation here. And the concept of confidence interval for y0. So we have studied confidence interval for usual, the one sample, but in the regression context, what happens? So we have the truth. So truth is, for example, the mu in usual, the univariate analysis, but in linear regression context, the truth is y is equal to a plus bx. And if we fix the x is equal to x0, then it's no longer, the linear function and just the one section. So a plus b times x0 is the truth. And the truth is not observable. So given data points, such as these 5 data points, that we can estimate the regression line. That is y is equal to a hat plus b hat x here. And this regression line that depends on the data. So if data changes, then regression line changes. And suppose we have the different 5 points, just the same number of observations from the same data generating process, then we have different regression line. So I draw 3 regression line here, and this 3 regression line is included. I mean, the intercept of this regression line at x is equal to x0 is included in this interval. And if this interval includes the 95% of the all, fitted regression line with the 5 data points, then we say that this is the confidence interval for this regression line. So we have to be given the sample size, otherwise larger sample size gets more accurate line. But given the data size, this is the definition of confidence interval. So 95% confidence interval includes the 95% of intersection of x is equal to x0 and the regression line, the blue line. So next, how to calculate confidence interval for y0. And basically, the intercept is denoted as the y0 hat. So because the y0 hat is the point on the regression line, so this is basically the important quantity to construct confidence interval. So we want to see how many percentage of y0 hat is in the interval. And what is the variance of y0 hat? So y0 hat, the expectation is x0, so a plus b times x0. So that's clear. So the important thing is the variance. So variance of y0 hat. What is variance of y0 hat? And y0 hat is equal to x0 transposed times beta hat by definition. So we defined the y0 hat. So best estimate when x0 is given. So that is y0 hat. And we know the variance of beta hat. We have derived formula in the theorem 2 of the same chapter. So that was x transpose x inverse times the sigma square. And in general, if we have some constant times some random variable, this constant can be out of this variance because constant that does not matter for this. So, and to be exact, so variance of this, we have to have the x naught, the transposed times the variance of beta hat times x naught. So if we describe everything component-wise, that you can see that why that this is true. So this is just a calculation. So then that we can get this is x naught transposed times the x transpose x inverse sigma square times x naught. But the sigma square is scalar, so you can put it at any place. So now that we can get the variance of y naught hat. Then we know expectation and the variance. And that we can also prove that it's known that the y naught hat is distributed with t distribution with degrees of freedom n-2. So if we use the quantile point of t distribution, so this the t sub 1 minus alpha over 2 is the coverage. So the quantile point that the 1 minus alpha over 2 of the observations are below this point. So if we think about plus minus the t sub 1 minus alpha over 2, so that has coverage of 1 minus alpha. So now that we can see that the range for y naught hat. So I would say the expectation of y naught. So expected value of y naught, the ranges from our estimate, the y naught hat, the plus minus the t sub 1 minus alpha over 2 times the square root of variance. So this gives the 95% coverage for expectation of y naught. So y naught hat is our realization, and this is the basically the margin. And here S is the estimated standardized residual. So the estimated residual standard deviation. So in R that you can extract this information by the summary of LM object of maybe $sign sigma. Then you can extract this sigma. And that is calculated by SS error. The SS error is the summation of the epsilon hat square. So summation of epsilon hat square, then we divide by n-2. Then we get S square, so we take square root to get S. So now that every quantity is clear, so we can calculate the confidence interval. Yeah, so expectation of y naught is within the interval, this interval with probability 1 minus alpha. Alpha is typically 0.05 or 0.01. So we calculate 95% and 99% confidence interval respectively. Okay, so next, the prediction interval. So confidence interval is for regression line. And the prediction interval is for observations. So this is maybe prediction interval is more intuitive. So prediction interval at x is equal to x0 means that if a new observation is on this red line, and 95% of the observations belongs to this interval. In such a case that we say this interval is 95% prediction interval. So this is kind of the error band in the usual sense. The 95% of observations that fall in this range if x is equal to x naught. How to calculate prediction interval for y naught? And okay, so we start with the original linear model. The y is equal to x beta plus epsilon. And so basically for new y0, that we have the two variability. So one variability is in estimate of beta. So beta is only estimated. So beta had some variability. And also the epsilon naught. So this is a kind of the intrinsic error. So we cannot avoid even if the model is perfect. So epsilon also have some, the variability, randomness. So if we think about the estimating y0, then the y0 hat is equal to x0 transpose times beta hat plus epsilon naught. Okay. So the both beta hat and the epsilon naught have the randomness. And the beta hat is estimated based on the existing observations, and the epsilon naught is based on new observation x0. And the assumption of the linear model is that all observation, these n+1 observations are all independent. So that means that these two quantities, beta hat and epsilon naught, are also independent. So independent, so we can calculate the variance separately. So variance of x0 transposed beta hat, that is what we calculated in the previous slide. Then what is the variance of epsilon naught? So epsilon naught, actually the variance is sigma square. That is the definition of the model. So we add sigma square. So that's why we add 1 here for prediction interval. So prediction interval is for observations, so it has more variability. So confidence interval is for the mean, expected mean, so that it has the narrower band. We only have the uncertainty in beta hat. So in similar way that we can develop the formula for prediction interval. So everything is the same except for this one. So actually this one is pretty large usually. So in many cases, so the prediction interval is much wider than the confidence interval. Yeah, so one note. So which one should we use, the confidence interval or prediction interval? So we have two similar things. So prediction interval that shows the variability of y0 in the usual sense as an observation. So we can see how much variability the new observation has. We can predict that. And the confidence interval is for the expectation of y0. So if we have many new observations whose x values are x0, then the mean size, the sample mean of their y value is likely to be in the confidence interval. So that is the difference between the prediction interval and confidence interval. Prediction interval for observations, the confidence interval for regression lines.